All right, so in chapter 18 of Math for the Non-Mathematician, we are presented with this idea of uh, this wonderful drawing over here where we have a weight that is suspended from a spring that's attached to some sort of stand. Okay, so that's what that is supposed to be. All right, so that's our suspended weight that we can then, I don't know, oscillate. Um, and as we do that, we can record its position through time. Okay. And what we're going to do is we're going to start at 0 right now. This is our, equilibrium point. I know my drawing, the string looks pretty stretched out, but let's just pretend that it's not. So, right now if you have a spring, you have two options. You can either stretch it out and let it go, or you can push it up and let it drop. Uh, for our purposes, we're going to push it up and let it drop. So as we go, we're going to push up our spring, and this is, we're going to actually push it up somewhere over here, and so now we're going to be drawing its actual movement, because if you push it up, obviously, then it's going to jump way up here, but we're not going to focus on that for right now. So this is later after it's established its pattern, and we're assuming, there's no air resistance or anything like that, all this stuff that is going to apply to a real life situation that you have to worry about in physics, but in math we don't have to worry about those things because, you know, sorry, we think about these things theoretically, and so we don't have to worry about air resistance or friction or things like that. So anyway, our weight is bobbing up and down, and so as time goes, it gets higher and then lower and then higher and then lower and then higher and then lower and then, and it just continues. And if you can actually draw nicely, this is going to turn into a regular, predictable shape. Okay? So pretend that all of those things are nice and even. All of the top points, the crests are nice and even. The troughs are even. If we were talking about sound, they'd be the wavelengths. Those should all be nice and even. Okay, so pretend all those things are nice and even, and it's all regular. Of course, I can't draw very well, and you guys know that. But what we have here is a sine function, or it's also called a sinusoidal function. Okay, so this is what happens when you graph the sine of something. Now, as you can see, the weight is going to go up, and it's going to go down, and it's going to go up, and it's going to go down, and it's a nice cycle. Okay, it's repetitive motion happening over time. So since we have a cycle, one really easy way for us to then find the values of these, because it's a graph, all these points here up and down are going to have numerical values, is to look at what's called a unit circle. So we've got that out of the way. I'm going to try and do this one a little bit better here, guys. You know what? I'm going to do... Those are not... Look! It had three-dimensional graphs the whole time, and I didn't know that. I'm sorry. Trying to draw... That's a pretty decent circle, and now I will draw my grids through the circle instead of the other way around. So again, we're going to pretend that that's nicely centered. And we're going to pretend that this circle has a radius of 1. Okay, so now wherever we are in this circle, we can always, here is 1, here is 1, here is 1, here is 1. Wherever we are, we have a radius of 1. With that, we can draw triangles and find the sine and cosine. The sine and cosine are then going to tell us the coordinates of, like here. So this is 1. The coordinates here, this gives us a right angle. We're going to assume that this is 30 degrees and this is 60 degrees. And then now we have our x and our y, and our x and y give us our coordinates, and that gives us our position on our circle. Okay, another way that we can approach this is if we have our x and our y, we know our position on our circle, we know that our diameter, or I'm sorry, our radius of our circle, and therefore our hypotenuse is 1. We can then work backwards because we'll know that the sine of theta is y over 1. The cosine of theta is x over 1. Okay, so then once we know what x and y are, we can then find our angle. Okay, so that's going to be helpful for us. Now there are some special angles that we have in our circle. All right, so we have some special angles in our circle. If our point is right here, we know that we're at the point 1, 0, right? So our sine, well, our theta is 0 because we're right along the x-axis. Anytime we're looking for a theta, we are talking in relation to the x-axis. We're always measuring from x. We're never measuring from y. But anyway, so if our we've got 0 here, our hypotenuse is 1. So our sine, well, we know, we can just tell by looking at it that for 0 degrees of 0 degrees equals 0, right? Because our opposite, our angle would be here if there was one. The opposite is 0. The y value is 0. So 0 over 1 is 0. Okay, so the cosine of 0 degrees is the adjacent, so it's 1 over 1 because our hypotenuse is 1 and our adjacent angle, the x value, is, or our adjacent leg, the x value is 1, so our cosine is 1. And our tangent, opposite over adjacent, we've got 0 divided by 1, so we've got 0. Okay, so those are sine, cosine, tangent if we are working with an angle of 0. That's very helpful. However, what if now instead of 0, we are working with 90? Okay, and our point is here. So now we have the sine of 90 degrees. So now our x value is 0 and our y value is 1 and our hypotenuse is 1, because even though we don't actually have that third side, we're going to pretend that it's it's infinitely small third side, but we still have a third side and it's 0. So we still have this imaginary triangle, it's just, very, very, very narrow. But anyway, so when we have here, we've got the point 0, 1. Our sine is going to be, again, here's our angle that we're measuring from 0. So our y value, right, sine is always y over 1 in a unit circle. Our y value is 1, hypotenuse is 1, so sine of 90 is 1. Cosine of 90 is going to be x over 1, which is 0 over 1, which is 0. And then our tangent of 90 is going to be, y over x, which is 1 over 0. We know that we can't divide by 0, or at least when we do, it gets very messy, and so this is undefined. There are some various other functions, other ratios that are undefined. It's just our first one that we're coming across is the tangent of 0. Now, in the previous video, I mentioned the sine of 180 degrees, and I said that was a bad example because 180 degrees was special because it's contained in this unit circle. It's a special place on this unit circle, and that is over here at -1, 0. Okay, so 180 degrees is this place -1, 0. So sine of 180 equals, right, so y over 1. Y is 0 over 1 equals 0. well, -1. So cosine of 180 equals x over our hypotenuse. So we've got -1 over 1, that's 1, equals -1. And tangent of 180 is opposite. Y over x, sorry. Y over x is 0 over -1 equals 0. Okay, so you'll notice that these are very similar values to here, right? Except that our cosine is negative. Because remember, we're always measuring our angles from the x-axis. So 0 and 180 are what are called reference angles. Okay, so we can, we'll get to this more in a little bit, but we can actually measure from these points. Okay, and so now we have our last point that you can see in this series down here of 0, -1. So this is, hopefully you can see that it's going to follow another pattern that we might already have established. So sine of, this is 270 degrees, equals y over 1 equals -1 over 1 equals -1. I'm writing inside my unit circle, but that's okay. Cosine of 270 degrees equals x over 1. Again, the over 1 is the hypotenuse because my circle has a radius of 1. So 0 over 1 equals 0, and then tangent equals y over x, of 270, equals y is -1 over 0. And so now this is undefined. So you can hopefully see that this has some similarities, that is a bad circle, to 90, right? So we have got the -1 and the +1, the 0, whoops, 0 for cosine and undefined for tangent. So we've got these kind of opposites where the numbers are the same. It's just our sine and our cosine are switching their signs from positive to negative. So hold on just a second. Sorry. Okay, so this is my lovely chart. The one from the previous lesson was a little obnoxious, so we're going to just draw it. Okay, so here's my lovely chart. Like the special triangle chart, so we've got sine, cosine, tangent over here. So the sine of 0 degrees is 0. Sine of 90 degrees is 1. This is going to be a really good chart for you to copy and memorize and work on. And then also, additional thing to think about. So we're working in this unit circle, right? We go 0, 90, 180, 270, and then back again to 360. So this is 0 degrees, and it's also 360 degrees. Okay? So those are the basics of the unit circle, but the unit circle also does a whole lot more. All right, so let's say that we need to find the sine or cosine or tangent or whatever of 150 degrees. All right, now 150 degrees isn't exactly at our 90, 180, or 270, and it's not specifically at a 30, a 60, or a 45 degree angle. Or is it? Okay, so if we look at our math for non-mathematicians, if my computer will cooperate, 150 is between 90 and 180, right? So okay, so 100. So we're going to take this function 2. Sorry. Oh dear, I lost my spot. There we go. So we're taking this formula too. Sine of A equals sine of 180 minus A. So we are, really what we're doing is we are taking a reference angle. So we want to know what x-axis, how far away is it from an x-axis. We really don't care which one, and we don't necessarily care at this exact second if it's above it or below it. We just want to know how far away is it from one of my x-axes. Well, I guess there's really only one, but okay. So it's past 90, so we're going to subtract it from 180. 180 minus 150 gives us 30 degrees. So we're going to draw a 30-degree angle-ish out from here, 30 degrees, 1. All right, so now we have, supposedly, this is poorly drawn, but just label your angles and it'll be fine. A 30-degree angle, a 30, 60, 90 triangle out from, our starting point, right? So we know the values of 30, 60, 90 triangles. And so that's going to put this one at negative square root 3 over 2 and 1/2. Okay? Because of the ratios of the sides from the 30, 60, 90 triangle that we studied previous days, we know that this is its point. So if we need to find the sine of 150 degrees, we're taking the y, not parenthesis, y over 1, or 1/2 over 1 equals 1/2. Okay, and if we need to find the cosine, it's x over 1, because the hypotenuse is 1, so it's going to be negative square root of 3 over 2. And if we need to find the tangent, we're going to do y over x, and that ends up being negative 1 over the square root of 3. Okay, so that all of those numbers coming from special triangles from yesterday. Okay, so now let's look at finding sine of 225 degrees. Nope. 5 degrees. There we go. Okay, so 225 degrees, it's more than 90, it's more than 180, but it's not quite 270. So we're going to look in Math for the Non-Mathematician. It is between 180 and 360. So we're taking negative sine of A minus 180. Back to my correct thing. So negative sine of 225 helps, minus 180. And so that gives us 45. So now we draw a 45-degree angle. And we have a 45, 45, 90 triangle down here in quadrant 3. All right, again, we've got our hypotenuse is 1, and we know from our special triangles, now we're in quadrant 3, everything is negative. So we've got negative square root of 2 over 2 and negative square root of 2 over 2. Okay? And then from there you can find, of course, the sine, cosine, and tangent, with the sine being y over 1, cosine being x over 1, and tangent being y over x, which in this case, since they're the same, is going to be 1. All right? And so similarly, that's what you're going to do for all of that big, nice, long list. If you have any numbers that, say, are over here, like 300. Okay, so that's where I believe for each, yeah, so 360, you're going to do A minus 360, so you're going to end up with negative 60, and that's going to give you not a 60-degree angle, about more like that one. Okay, and so then now you have 60 degrees over here, and you can go from there. Okay, so look at those formulas from the Math for Non-Mathematicians, and based on what quadrant you're in, you'll know what kind of subtraction you need to do. You should, at this point, be getting all 30, 60, 90 triangles, or all 45, 45, 90 triangles, because again, we're looking for a reference angle to know what quadrant to draw it in. Hint, if your answer ends up being negative, like here, 300 minus 60 gives us negative 60, or I'm sorry, 300 minus negative 300 minus 360 gives you negative 60, so we know our angle is going to be negative, okay? Our triangle is going to be down in the bottom quarter. You can also just think, well, 300, it needs to be somewhere in quadrant 4. You can just reason it out that way. Okay, so the other thing to remember is that if your angle that you're working with is over 360 degrees, it's just gone around. Your weight has bobbed a certain number of times, and so it's just gone around the circle multiple times. So like if you had 720, well, you go around once and that's 360, and twice and that's 720, so you're still at the point 0, or I'm sorry, 1, 0. Okay, so what you want to do is always on this first section of the homework, be figuring out what your reference angle is. Is it 30? Is it 45? Is it 60? Is it 30, 45, 60 from your negative x-axis? Is it negative 35, negative 30, negative 45, negative 60 from your negative x-axis? So those are the triangles that you're looking for. Those are the angles that you're looking for. Sorry, I know I'm erasing everything. So that's generally, functionally, mathematically, what you're looking for at this point. Okay, I don't think Math for the Non-Mathematician goes so far as to like actually, yeah, so here it says express the following sine value as signs of angles between 0 and 90. So it's not actually asking you at this point, I don't believe, to find the sine. It's just saying express them. So like sine of 390 equals the sine of 30. That's all it's asking for at this point. But we've gone through, and you can kind of see how the unit circle helps you find those values, and we'll come back to those another time.